Cool. I think we can now resume. So I just mentioned that the Wreath product between symmetric groups is less interesting. This is because in general, this is not a complex reflection group. So if you know this theory a little bit, you know you can define, say, Hecke algebra on any complex reflection group or rational Schrödinger algebra and such and such. So I mean, up until now, complex reflection groups are considered the most interesting family. We will see that definition later. But this, I think, in group theory is just considered like the most general thing you can do on finite Wreath product. But as I said, we just discovered something interesting on this group on the algebra level. So what we are doing here is to give a definition. This is due to myself and my collaborator Dan Nagano at UGA and Ziqing Xiang in SUSTAC. So this notion we call the quantum Wreath product can be thought as a quantization of this process. You actually start with an arbitrary associative algebra. You take subject to some choice of parameter this process, and then you obtain a new algebra. Sometimes you can embed this guy into a larger Hecke algebra, but in general, we don't know what's the precise condition here. We only have examples. And furthermore, they are more interesting examples that cannot be embedded into a finite Hecke algebra. So this may not be something we should pursue. And let me tell you some of these examples that we are considering. So the first one is when B itself is a Hecke algebra of type A. Then through this process, we produce what is called the Hu algebra, due to Hu Jun in his 2002 paper regarding Morita equivalence theorem on Hecke algebras. So you can define something that's embedded into a larger Hecke algebra of type A, and we'll talk about this guy, say, in the next hour. And we have found some interesting evidence that we think this guy should be now viewed as the Hecke algebra for this Wreath product. So as I said, this is not a complex reflection group in general, and hence all the existing theory does not apply immediately. And then we hope that we can develop all the parallel theory for this guy, and then for this Wreath product between symmetric groups. And then we will talk about more connection to other fields for that uses this algebra. And then the next example is when B becomes infinite dimensional. If you take any commutative ring K and you consider the Lorentz polynomial, you can actually obtain the affine Hecke algebra using this quantum Wreath product. And then you can take a surjective map to recover the Ariki-Koike algebra, which is a certain quantization of this generalized symmetric group. then you can they'll also consider a degenerate version of these algebras, starting with a base algebra, which is just a polynomial ring. By choosing different parameters here, you get either the degenerate affine Hecke algebra or the neo-Hecke ring due to Kumar and Ginsburg. And for myself, the significance here is this neo-Hecke ring actually keep tracks of the Hom space of KOR algebra. I will talk about more connection that you can go from this direction. And then for some algebras in more generality, you can start with, say, any associated algebra, and there is a procedure due to Kleshev and Robert Muth 4 years ago. They call this procedure affinization algebra. And this is, I think, rather vague, but they have only one interesting example in mind. This is when the B itself is a zigzag algebra. So by taking the affinization, they recover something that they use to understand the imaginary strata of KOR algebra. This can be considered as a generalization of this. So you are taking a zigzag algebra over this ring of Laurent polynomials, and then you obtain something more complicated, and they can study the imaginary strata of the KOR algebra by studying in the representation theory of this affine zigzag algebra. They are also the case when B is any Frobenius algebra, which has some connection with TQFT, topological quantum field theory, if you ask. And then there's a general procedure due to Russell and Savage. This is also very recent. What they call is the Frobenius Hecke algebra, or its affinization. And in particular, if you take B to be the group algebra over this polynomial ring of any finite group, you obtain the so-called Wreath Hecke algebra due to Wan Jinghui, Weicheng Wang. This is a sort of degenerate affine Hecke algebra for this Wreath product G with the symmetric group. And then we just learned that recently. You take B to be any commutative ring, then it is possible to relate this quantum Wreath product to Ben Elias Hecke type category. So I'll explain this connection maybe on Friday. So all I'm trying to say is now we have something that seems to unify all the previous result, but we also include a new addition to the family of Hecke type algebras, which is the Hu algebra. and we are going to study like the conditions, whether you can push from the existing theory on the algebra B to the new algebra constructed this way. So what we are trying to do is to determine conditions. Sometimes if and only if conditions, sometimes you have only one directions, such that the structure or representation theory of B can be upgraded to those of the quantum Wreath product. And let me just list a few of conditions we have in mind. The first one is the problem that I'm going to explain today, the one cover problem of the Hecke algebra for complex reflection group. And then we are considering the geometric representation theory for the Wreath product between symmetry group. So we expect that there are some semi-new geometry. So this is essentially still the type A geometry, but you have some like higher level viewpoint. And then you have what? You have a connection with Elias generalized KOR algebra. And then you can talk about some McDonald identity say something other than the invariant part of the affine Hecke algebra. This is some ongoing like discussion with yeah. Anyway, I'll talk when it comes when it comes to that part. Okay, so are we all happy so far? Any questions? Yes. There's no actually no there's no difference. So, oh yeah. So this like this imaginary strata is not it's exactly the algebra. So so by clear, I mean there are some like missing steps. So you take the zigzag algebra, you obtain something they call the affine zigzag algebra, which is used to explain the theory about imaginary strata. So this is not that thing yet. So in that sense, I should really write double arrow here because this is the Wreath Hecke algebra. Yeah. Oh no. So in KOI algebras, they are sorry, I losing my so I'm holding for now. So they are real roots and imaginary roots in an affine root system. So imaginary part corresponds to those imaginary roots. Try to fix this. Okay. Okay. Oh, all right. Other questions? If not, let's talk about all the existing theory of a finite Hecke algebra. And then just to remind you, we are having the intention to generalize everything whenever it's possible to all these variants of Hecke algebra when it's possible. So the beginning is the study of Chevalley group. So the finite Hecke algebra is first introduced by Iwahori and Matsumoto in about 64 to 5. And they introduced the finite dimensional Hecke algebra from the study of Chevalley group over finite field. And what they prove is that, firstly, this Chevalley group has a BM pair. In other words, there are groups, subgroups of this guy, so that the quadrupole G, B, and W forms a TIT system. So for a TIT system, it has to be that the group G is generated by B and N, and then you can take a quotient of M by B intersection with N. So in order to make this well-defined, you require B intersect with N to be a normal subgroup of this N. So then you have a well-defined quotient group. And furthermore, this guy has to be generated by a bunch of generators. Each generator has to be an involution, which means it squares to identity. And then there's a axiom that if you take this coset, it has to satisfy that this lies into the union of those double cosets or any W inside this capital W. And furthermore, each generator, Si, does not normalize the group B. So these axioms are needed so that you can define the Hecke algebra for the pair GB. So as a vector space, it is the span of those standard bases. So for convenience, let me use C to be my ground field all the time. And by this, I mean, I want to construct these TW explicitly so that this becomes a group algebra of this Chevalley group. So you take a sum of all the element in this double coset. So you get an element in the group algebra, and then you divide it by the number of elements or order of B. So this only makes sense when B is over finite fields. So you do some counting over finite fields. Otherwise, this is not defined. And then this, let me give it this a name. This is what we call a standard basis. And from here, this W we define is a Coxeter group. So you can look at these Coxeter groups directly without going through any such Chevalley group over finite field. So by a Coxeter group, I mean this has a presentation of this form. You want to mod out that S squared equals to identity, and then you want to describe the relations using so-called Dinking diagram. And then a Coxeter group is equipped with a length function. It is defined this way. So a length of any element in a Cox group is equals to the number of reflections in any reduced expression. Let's see. So by reduced expression, I mean this is any shortest among all possible expressions, and I will use Wreath for short afterwards. How about this? Okay, good. Okay, so this is like the very first definition of a Higgs algebra, and you can notice that in this setup, Q seems to be the number of element in your finite field. But this is not really an obstacle. You can actually define something we now call a generic Higgs algebra, or just a Higgs algebra, to recover this Higgs algebra coming from a Chevalier group. So, what is known is this is a specialization of generic Higgs algebra. So now by generic, we mean that we can choose Q to be an invertible element in my ground field, and I like it to be C for simplicity. And so for any Cox group, I can define a Higgs algebra using a similar presentation. So I want to label my generator using Ti, and then I quotient out the same braid relation by the thinking diagram. And then I want to upgrade this quadratic relation. So it used to be Si squared to 1, but now I need Ti squared is equals to Q minus 1 Ti plus Q. So when you compare the two, you see that this recovers the previous one by setting Q equals to 1. And also it matches with this finite field construction. So if you do some, say if you use the standard basis from this definition and compute, say, the square of T corresponding to Si, then you get exactly that formula. And then one can show that this doesn't matter. The Q can be any invertible element in your ground field. It doesn't have to be some number corresponding to the order of your finite field. Okay, and then from this definition, we can play some game in arithmetics. So you can define the standard basis TW from the fact that this element is well defined when you choose any reduced expression for W. You take the corresponding Ti and multiply then. So you can actually show that since the braid relation hold, no matter which reduced expression you choose, this element defined this way is the same. And then you obtain this standard basis. And also I want to remind you from this quadratic relation, it is easy to deduce the inverse formula for the generator Ti, because you just like pretend they can be invertible already, and then you multiply Ti inverse on both sides, you play some game, and then you can get that Ti inverse has to be Q inverse times Ti minus Q minus 1 once you obtain this, you can actually check that this is the inverse for Ti by left and right multiplication of Ti. Then you can verify this is indeed the inverse. And what's so important about this is that there is a consequence of having a nice involution we call the bar involution. So you want something that can be defined on the Hicke algebra sending Ti to Ti inverse. And then you want this to be an involution, and hence for any typical element in the Hicke algebra, this has to be the inverse of W inverse. And then this bar involution has to send Q to Q inverse for some reason. Okay. Next, we have a symmetric Frobenius algebra structure. So this is not the symmetric algebra on a symmetric algebra on a vector space. This is symmetric in the sense that the corresponding Frobenius bilinear form is symmetric. So by this, I mean this is a finite dimensional algebra with non-degenerate symmetric associative bilinear form. And equivalently, it is useful to look at the trace map associated with this bilinear form. So you will only need a trace map that goes from the Hicke algebra to the ground field such that this satisfies the trace identity as you learned in linear algebra. And you can give a precise formula for this trace map and the bilinear form, which I will skip for now. And then let me say some upshot for having a symmetric algebra structure. So this is mostly used for starting the representation theory of the Hicke algebra. You know first that HQ as a module over itself is injective. So I hope at the end I can talk about some representation theoretic consequence of this. And then you also know that for any finite dimensional module over the Hicke algebra, projective is equivalent to injective. So spoiler, this will be used in the Schur duality for the quantum Wreath product, but we'll see. Okay, questions so far? Cool. So next. This is actually a continuation of the bar involution. So in representation theory or Lie theory, what is known about the Hicke algebra is that it has a unique Kastan-Lustig basis. So Let's denote this by C prime. And for better explanation, let me assume that you can find another invertible element in C. This is a parameter, formal parameter, such as this square 2q. So this characterization is that this basis element is firstly bar invariant, and then this, if you write it in terms of the standard basis, there's a unitriangular relation. So this is some v power times the same standard basis element, the standard basis element corresponding to the same Valgrind element, and then everything that shows up afterwards is smaller than w with respect to some order. And then the coefficient is a polynomial in V. Moreover, those coefficients are non-negative integers in V. And this is the case when you normalize your standard basis by some negative V power. But what's more important is this part. You have a positivity phenomenon in your unitriangular relation. So, oh yes, you're right. Thank you. And then I'll be vague here. This is, maybe emphasized over and over in the last 30, 40 years. The upshot is these coefficients describe irreducible characters of Lie algebra having Weil group W. So this is rather weird. So you are now looking at the structure theory of some algebra, and then all of a sudden you're saying this understanding of this guy can be used to study the representation theory of the Lie algebra, which is a seemingly unrelated algebra. But this is like, I would say, a mathematical miracle in the last century. And then we'll see some other viewpoint that can maybe convince you that it is important to establish or trying to establish a parallel basis theory for those new algebras. Okay, what's next? Okay, so I would like to draw you a picture why, say, the Lie algebra is related to the Hicke algebra in this sense. So this all go back to the thesis work of Isaac Schur in more than 100 years ago. So what Schur did first is trying to mimic his advisor Frobenius' work on the representation theory of symmetric group. They want to study the polynomial representation theory for general linear group, and what his approach can be now rewritten as the follows in today's language. So you want to look at some coordinate co-algebra. So in this sense, co-algebra structure is more important than the algebra structure. And then you have some sub-co-algebra of this guy. So though they represent, say, the polynomial representation and also the degree D homogeneous representation, but let's not care about those at the moment. And since you have everything on the co-algebra side, you can take the linear dual and look at the corresponding algebra. So you have something over here, and the inclusion is translated into a surjected map. So this is how Schur defined at the first place his Schur algebra. This is just the linear dual of this subcoalgebra. Yeah, let me use subscript for consistency. And then this U, at the moment, let's not care what that is. This act naturally on some bimodule of UN as well as HD. So we secretly use H because we want this to be a Hecke algebra or its specialization. In sure duality, the first case, this H is actually, say, the group algebra of symmetry group. And then the bimodule is a UN HD bimodule. And if you have such a picture, the outcome is we should be able to study representation theory of these simultaneously. And in Schur's work, he actually proved that in 2 papers. If you take the degree D representation of UN, then this is equivalent to the co-module category of AN, and hence the module category of the Schur algebra. So, like I said at the beginning, this is polynomial representation of GLN, and the corresponding algebra here is the universal envelope algebra of the Lie algebra. So what's difficult for these guys is that they are all infinite dimensional. So the first question is how you deal with this infinite dimensional algebras. This is supposed to be a difficult question. However, when you do this process, you obtain something finite dimensional. This is now much more accessible from compared to the infinite dimensional algebras. And this is one powerful upshot of a Schur duality. You reduce the study of representation theory of something that's more complicated into a finite dimensional algebra. So you can use all these theory about finite dimensional algebra for studying the representation theory altogether. And then the next upshot is now we have the connection vertically. I really want to connect the representation theory from here to our Hecke algebra or its variations. Okay, so what's also known is if there's a condition on n, if n is greater or equals to d, then the double centralizer property holds. So I think this is what is known as the Schur duality and that's the most adopted notion of a Schur duality. So you want, let me skip the subscript for now. You want that the 2 actions commute on your bimodule, and then if you take the centralizing partner of 1 action on the bimodule, this is all the endomorphism on the bimodule that commutes with, say, the H action. then this must be all the actions coming from the other side. And vice versa, if you take the centralizing partner of the S action on the tensor, I should say bimodule, and then you get the other algebra. And an upshot is you can use the, maybe this is something you learned from graduate algebra, that this bimodule has a decomposition into SH bimodule. And these L sub lambda, S sub lambda are irreducible module of over S or H. And then this gives you further a homological way to understand this Schur duality. You can now take the Schur functor, which is defined by taking the hum of your bimodule. So this is a functor going from the module category over S to the module category over H. And in particular, it matches those irreducibles. And I think they are also consequences from this homological construction. So there are people studying these Schur functor, their right adjoint, left adjoint, the right derived functors, the corresponding spectral sequence and such. So there are plenty of things to do about this homological viewpoint. And then finally is we talked about the Cauchy-Lussick basis on the right-hand side for the Hecke algebra. There is a formal procedure to produce from the Cauchy-Lussick basis of H to canonical basis of some algebra related to U. But this is not what I'm pursuing for today, so I'll just leave it there. Okay, are you all happy so far? Questions? Okay, next one. So we so far talk about only the structure theory of the Hecke algebra, and let me talk about a standard way to study the representations of the Hecke algebra. So to do this, one good way is to actually use the cellular algebra structure. So this is a theorem due to Geck. So by a cellular algebra, you actually need a cell datum consisting of a poset, some map I will describe later. Oh, by the way, the term cellular algebra is due to Graham and Lechler in '96. So this is this gives you information about the H irreducibles. So they can be constructed from all the non-vanishing cell representations. So I only give you a flavor here. From this datum, you can find a way to describe those cell modules. Sometimes they are zero, sometimes they are not. And those non-zero cell modules form all the irreducible modules over the cellular algebra. And then you can use these information to detect simplicity of the algebra. using decomposition number. And then, decomposition matrix. And then you can also relate this algebra to another important family of algebras, which are known as the quasi-hereditary algebra. So let's look at one interesting example. This is the basic one when W is the most fundamental vowel group, say the symmetric group on n letters. This is the type A case. And the cell datum is nothing but the partition of n. And also this M gives you a label consisting of all the standard young top low of the shape lambda. And then you can define a cellular basis So it has now two parameters, S and T. They are standard young top low for the same partition. So on one hand, you know that the Hecke algebra of type A is a quantization of the symmetric group algebra. So there is already a known notion of the Speck module. But now here, you are all of a sudden identifying each basis element. Sorry, let me start over. So let me start with the basis first. So the cellular basis is now indexed by a pair of standard young top low. But we talked about the type A case already. You see that these Hecke algebra, it has a basis labeled by the vowel group or the symmetric group. This gives you a representation theoretic upgrade of the bijection known as Robinson-Shenstedt algorithm that maps a symmetric group bijectively to a pair of standard top low. And this is reflected in this cellular basis versus standard basis business.
So what's the star?
Well, the star. This is the map sending TW to TW inverse. This is similar to the bar involution but without the inverse. And star is an anti-automorphism. C is the assignment going from these data to a basis element of the cellular algebra. So
the algebra structure is some kind of intersection figure of the cellular basis, or what?
Say your question again.
The algebra structure in some sense is the intersection theory of the cell.
Yes, exactly. Yes. So I think this is motivated by the study of Cassandra-6 cells on the Hecke algebra, but they formalize this to an abstract setting. So this cellular algebra encodes some other variation of the algebra. For example, Schur algebra are also cellular, but we don't need it for today. And there are also some recent papers, I think by Anderson, Strappel, Tupenhauer, saying that you should really consider only the algebra from the endomorphism of a tilting module. They say these are all the important cellular algebras, nothing more. That's the spirit of their recent paper. Okay, so I'm sorry to bump you with all sorts of definitions, but there are a couple of more that I want to talk about. So this is the cellular algebra structure, and I just tell you, I want to look at a quasi-hereditary algebra structure, but unfortunately, the Hicks algebra is not a quasi-hereditary algebra.
So may I ask?
So yes.
Now say type A for BCD, we still have some kind of cellular algebra.
They are all cellular.
Yeah.
So as long as W is of finite type, this is a paper by Geck, that they are all cellular algebra. So this is just one example, but they are all cellular algebra. I think one thing that's worth mentioning is that the cellular structure is not unique, and hence there is not a unique way to construct these irreducible modules. Yeah, so Geck has one cellular structure for the Hicks algebra, but there are also other cellular algebra structure, I think from deeper James and also Hookeer. So I think this is not canonical at all.
But the underlying algebra structure is always some kind of intersection of cell.
Yes, yes. Mm-hmm. So one upshot is you can actually determine semi-simplicity of your Hicks algebra. So when Hicks algebra is semi-simple, all the simple modules are, all the modules are, finite dimensional modules are a direct sum of simple modules, and the extension information is actually boring. All the X groups are 0. So what is more interesting is to study the representation theory of your Hicks algebra when this is not semi-simple. And then this is, let me write down what I just said. And a canonical way to do this is to find a quasi-hereditary cover of HW. And in words, this is 2 approximate numerical data of this module category from those data of a nicer algebra. And this is the quasi-hereditary algebra. I shouldn't say there are many choices. This is some quasi-hereditary algebra. So let me give a definition first. So this is a ring theoretic definition. So an algebra A is a, let me use QHA for short. This is a quasi-hereditary algebra if there exists a chain of ideals. Such that each quotient is a special ideal of the larger quotient. So I will only say it in words because this is not very important. So this means this is idempotent and this one condition. So this guy multiply the radical and then multiply itself is, I think, 0. And anyway, so don't quote me on that, but this is not what we are going to use here. So this ring theoretic definition makes sure that this algebra has finite global dimension. So by a finite global dimension, I mean the X group information is quite limited. There is a finite number such that all the X information above that number is 0. So this is almost telling you that if you want to look at these module categories in which the X information can be hard to describe, you can always try to find some related numerical data from a module category over some algebra with finite global dimension. So you have a rather nice X information.
So what's the cover, please?
Cover.
Yeah,
I'm going to explain that. So the cover tells you how to relate from one module category to another, because we are only talking about the algebra itself. You need to know what's the relation between their module categories. Actually, I think maybe we can take a break first. So we'll resume at 2:10. Quasi-Hurday algebra, we actually don't really care of the algebra structure. So what is proof? And this is what we want to think of is you want to look at the corresponding module category. This is now a highest weight category in the sense of Klein partial Scott. So this is an axiomatized version of the category O of the Lie algebra. So for this definition, you need first a set of standard modules labeled by a poset, interval finite poset, such that the endomorphism on each standard module is of dimension 1. And then if you have non-zero homomorphism from one to another, this is indicated or detected by the partial order on your poset. And then if you have some vanishing information on one module, if all the hom from standard modules into some module is 0, then this module has to be 0. And finally, you can define a projected module for each such standard module. And then if you look at the kernel of this projection, this has a delta filtration, which means the module has a filtration in which each quotient is isomorphic to some standard module. And then this motivating example is, as I said, this is motivated and then axiomatized by the category O for Lie algebra. So some upshots. Once you have an abstract highest weight category, you can ask what are the conditions. So this category has a Kashtan-Lussick theory, which means these decomposition numbers of a composition multiplicities can be determined by some polynomials coming from these Kashtan-Lussick polynomial or its homological version. So there are some deep theory concerning these highest weight categories. And for example, there are some study for Lie superalgebra that also uses analogs of a highest weight category. And next, what can we say about the module category of the Hecke algebra? Because we know that when this Hecke algebra is not semi-simple, this is not quasi-hereditary. However, it's a theory by Delap and Ringo. That every finite dimensional algebra has a quasi-hereditary cover. So that means you can always find a nice algebra and try to relate its numerical data to those of your finite module category of a finite dimensional algebra. So by a quasi-hereditary cover, I mean this is a functor from O. So let me write this functor f. And this f is constructed by taking the hum of some projective module. This is a functor from this category O to your A module. So first of all, this O has to be a highest weight category, which I defined over here. And as a fact, this must be equivalent to some module category for some quasi-hereditary algebra. And then this module P is a projective S module. And then your algebra has to be the endomorphism of your projective module. And furthermore, you have a hum condition. So if you still remember, this formula looks familiar. We talked about a similar functor in the last hour, which is the Schur functor. And indeed, a quasi-Herder cover started with Schur functor as the most fundamental example. There are some more complicated ones, but this is basically another axiomatized version of our Schur duality. So we have from any SND module to a symmetric group algebra module. And this is obtained by sending M to this hum, or equivalently hidden by an idempotent.
So in some sense, this kind of idea really is some kind of similar to Fourier-Mukai transform. So in some sense, one side is a space I, the other is a dual space.
In that sense,
plane wave is Fourier transform, and the idea, the kernel is up with the rho by P there. You are by module before, something like that.
Yeah, I think that they are vaguely related, but yes. Okay.
Because Fourier transform dual is the only evolution in your world. So everything should be related to Fourier transform.
Okay, so this is a theorem by Delap and Ringo. There must be such a quasi-Herder cover, but the downside is in their first construction, the cover is usually too large. You obtain something that's hardly giving you any of these numerical data. So the next question is, can you come up with a nice algebra that is small enough to do everything? And Hukier then proved that you can do it, and as long as you impose one more condition. So the statement is every finite dimensional algebra has a unique one cover. So this is the small and nice cover that does the job. And by a I cover, I mean,
So I missed it. What's the one?
I am trying to define here. Yes. So a quasi-heritage cover is an I cover. I is a number. So, and we will use 0, 1. You can also define a larger I cover, but we won't use it. So if you have an X condition, for modules admitting delta filtrations for also j less or equals to I. So for example, when I talk about a zero cover, I want to check a hum condition between these modules admitting a delta filtrations. This is slightly different than the hum condition here. Oh, sorry. I forget to write that this only holds when they are S projective. So you are looking at you want to look at hum condition on more modules in your category O. And when you talk about a one cover, you are not only checking the hum condition, but also the X1 condition on these modules. So this is the homological conditions you need so that your algebra is small and nice enough, and it is unique.
So I'm missing the last line. What's the J less than I? J is a gradient.
J, oh sorry, this is J. So when I say it's 1, you're checking x0 and x1 for, right. And then for example of a one cover, this is due to Hammer and Nakano. So it is actually surprising at the moment because people used to think that Q-shear algebra provides a nice quasi-heritage cover, as we saw there, but this is only true when the multiplicative order of the parameter is greater or equals to 4. So first of all, Q has to be a root of unity or a generic number. Maybe I should say Q cannot be, say, the root of unity of order 3 or less. When that's the case, this is no longer a one cover. So the Schur functor from the module of a type A Schur algebra to the type A Heck algebra is a one cover. Cool. And there are also other examples of, say, zero cover at a time. So this is a work by Ginsberg, Gui, Upton, Bukier. So they were studying the category O of rational Schrödinger algebra. you can think of this is also one highest weight category, but coming from a very different algebra. And they have defined a KZ functor by monodromy and some localization functor, which is rather complicated, which I don't want to define today. But what their work is, this complicated functor is a quasi-hereditary cover. And now let me explain what I'm doing here. So this W is a complex, any complex reflection group. So I have this Heck algebra defined for a complex reflection group. I also have this bold-faced H. This is so-called rational Schrednik algebra. And what's good about this is it has a category O because this algebra has a nice triangular decomposition. You can define it the same way as you did for the BGG category O for Lie algebra. And then there is a functor going from this category O as a highest weight category to the module category over Heck algebra. And these guys then ask a question. You have two functor. They are seemingly does the same job. That goes to the same module category in type A. Are they related, and in what sense? So you have this category O for symmetric group. You have the Schur functor from the Q-Schur algebra. Those are highest weight categories. And then they conjecture that these are equivalent as highest weight categories simply because they are both like highest weight category covers of the Heck algebra module category. And this conjecture is proved by Hukier when he established this idea of a one cover. Hukier showed that under certain conditions, under choice of parameters, this is a one cover. One cover is unique, and hence it must agree with your Schur functor. And so you have an equivalence of highest weight categories.
Could I ask a question?
Yes.
Why we don't have higher I over there?
Because it's in general not true when the parameter is not good. And when you have a two cover, it doesn't tell you, it doesn't give you like more information. As long as you can check, this is a one cover, this is already unique. By checking a two cover, it is still a one cover and hence is unique. So this tells you that you only need to check up to one. You don't need to check like more than one.
But the higher I means it's quite impossible to have that. So what is the easy one?
Like I said, if it's a two cover, it is already a one cover and hence it's unique.
I know, but
yeah.
Two cover is something quite rare compared to one cover. It's very difficult to get. We cannot get easily two cover, high cover. So what's the problem with the higher? Why people are not interested in high cover?
They don't have examples, I think. So they started with the examples, then they can formulate these axioms. If you don't know the example at first, then
different formula. I cannot pronounce it. QHA, we have so higher extension.
right.
Yeah, I, N, whatever.
Yes.
But suddenly we only care about one or two. So it's really non-vertical.
No, I mean this is enough. By checking this is a one cover, this already tells you that there's a uniqueness.
I know
yes.
your issue, but the construction is not. Is more difficult than just one. That's my issue.
I still think that you don't need to check more than one cover, but yeah.
No, that's for uniqueness.
Right.
We try to have a construction. For example, two cover. If by one cover, definitely two cover is more tricky than one cover by nonsense. So why people don't care about 2 cover and 3 cover?
So the logic, if there's a 2 cover, it must be the 1 cover. So
I know,
yeah.
But we don't know 2 cover. I know 1 cover is easy. 2 cover is more difficult because 2 cover is a part of the 1 cover. So the issue still exists. That means 2 cover is impossible to construct, and why people don't care.
I disagree, but let's move on. We can discuss later. Yeah. Okay, so as I said, this conjecture was solved by Hook here for type A. This is then a question. To what extent can we generalize this picture to other complex reflection groups? So the first problem we have is, even for the Schur algebra, people don't agree on one single definition. If you check like Q-Schur algebras of type B, there are like multiple constructions. Each of them generalize a favorable property of a type A Schur algebra, but these generalizations are not isomorphic as algebras. So the question is, can we construct the Q-Schur algebra for each type, and what are the conditions such that we have a commutative diagram between these? So the purpose is, at least I personally think, the KZ functor is hard to control. The definition and also the structure of a rational Schrödinger algebra is rather implicit compared to Schur algebras and the Schur functor, which is just basically hidden by an idempotent. So you want to find such equivalence of highest weight categories, and to do that, the only way I know is to find a 1 cover from this module category here and apply Hook's uniqueness theorem. And so what we did is, for type B, this is done recently. And what we did is to construct a 1 cover from a one of these Q-Schur algebras of type B. And this construction is inspired by a Morita equivalence of the Hecke algebra of type B with a product of Hecke algebra of type A. So first of all, Morita equivalence means that there's a equivalence of categories of modules categories over this guy and module category over that guy. So you can convince yourself by thinking of the, say, index set of these irreducibles. This is described using bipartitions, which means here you need a partition for one number I and the other partition d minus I. So these 2 partitions form a bipartition. So you can imagine going back and forth between the irreducible modules from here to here. And so to go further, we want to look at the GGOR problem for complex reflection group of type GPPD. In particular, this includes type D, which is of type 2 to D. So the reason that we think this is possible is because there's a similar Morita equivalent theorem due to Hu Jun in 2002. So you can look at a type D Hecke algebra, and this Morita equivalence split into two cases when D is odd. This is a little bit boring. This is like the type B situation. When D is even, say 2n, you get an extra copy. Okay, let me use whose notation. So you have this type A part, but you also have some new subalgebra that plays a role in this representation theory. So if you know the index set for irreducible Hecke algebra over type D, this is a class of bipartitions, and it doesn't split when the partition, each part add to different numbers. That corresponds to this type A part. But when the two parts of the bipartition corresponds to the same number m, it has to split into two cases, and that's why you need this extra summand to describe when the irreducible representation splits from the same the splitting conjugacy classes. Okay.
What's the relation between actual am and I equal m?
So, right, you're right. So there is no I equal m here. So when I is m, you have something new. This is no longer a parabolic subalgebra.
Oh, so in some sense, am is different from sigma m?
Right. It's different from all of these. And in the case when D is odd, you don't get m versus m at all. Okay, so now this is the meat for today. We are talking about a new Hecke algebra with this AM. So, the idea is that this is the Hecke algebra for the Wreath product SM Wreath S2, such that this chain of groups quantizes to the chain of subalgebras. So this is actually difficult to construct a subalgebra of this guy, which recovers this Wreath product at a specialization Q equals 1. And to explain that, let me actually recall again the definition of a Wreath product. So this is a semi-direct product of D copies of your group G, your base group G, with a symmetry group. And the relation here is you can describe a typical element using either a D tuple of G, or you can, this corresponds to this part, or you describe an element in the symmetry group part, which is W. And the question is, how do you determine the relation between these guys? This is when you swap one W to another side of G, you change the index of this D tuple and leave W unchanged. A good way to visualize this is to look at the automorphism of a two-layer rooted tree. For example, if I want to look at a cyclic group of order 2, Wreath, SD, I want to look at a rooted tree which each subtree consists of 2 vertices. And they are D such trees. And so each cyclic group of order 2 swap each vertices of each subtree. And then you have one generator S0 here, that is the most important one. And also you have transpositions for those upper permutations, S1, S2, all the way to SD minus 1. And you can easily see that you have generator S0, S1 to SD minus 1, and this corresponds to a Weyl group of type B. And then we have another important example, which is this sigma m Wreath sigma 2. So this is the other extreme. You have only 2 subtrees. Each subtree has m vertices. So you have a subgroup acting on the first subtree, and then you can take a conjugation and have it act on the second tree. But you only need one part to generate a whole group. And so you need one notation for the only transposition up there. So let me call it T. So if you want to treat this as a subgroup of S2m or permutation on 2m letters, this T is actually the transpose. This is sending 1 to n to m plus 1 to 2m and vice versa. And so you can unravel these crossings. You can find a reduced expression by reading these crossings one strand by one strand. So for this guy, this corresponds to Sm, and then Sm plus 1 all the way to 2m minus 1. So when I write an arrow, I mean this is the product Sm plus 1 all the way to S2m minus 1. This is the first crossing. And then you take the next crossing all the way to the lowest one. You actually start with S1 and ends at Sm. So you have a segment of length m. You have m such segment. This is indeed the case. The length of this Weyl group element is the number of crossings, which is m squared. So you're really looking at this generator T together with the 2 parts, which correspond to a parabolic subgroup, to generate this Wreath product inside S2m. And then I claim this does not quantize easily. So even though this is true, if you do the naive quantization, this is greater, the dimension of this guy is greater than the number of elements in the group. So you have to find an alternative of this T in order to define your algebra AN. This is not an easy question to answer. So to do this, who has to consider a larger algebra to work with. He wants to deal with a two-parameter Hecke algebra of type B. So, I mean, I have two type of generators. The type A generators corresponds to the usual quadratic relation. But the type B generator is the specialization Q equals to 1. And then you can define the H part using the type A generator. And then one can define those juicy Murphy element this way. You start with U0 plus or minus to be 1. Ui plus 1 plus minus is defined from a previous one times some q power plus or minus a sort of conjugation of T0. So I really want to highlight the 0 in the middle. So this corresponds to something happening on the base algebra. And those red Ti are just position transferring operators. So this is giving you some information on what's the important part to look at. So from this definition, you can actually do a quick calculation. So let me skip the details. The idea is when you are left multiplying any element of this form. Sorry, I should say, if you start with any element of this form, you throw ui plus to the right-hand side, and the left-hand side is all things in type A. When you left multiply by T0, this must lie in H ui, the same thing, plus some higher order terms. And hence, you can define a unique element this way. So let me write it for short. U plus minus is um plus minus. This is rather technical, but this is whose first definition. There's an element hm in H such that U minus TT, which is that naive quantization, is in the coset um plus. And that unique element is defined, is what we call HM. So this is because in UM minus, you have multiple terms consisting of a T0. So you are left multiplying something like this, like iteratively, and then you will find a unique element in this coset by just multiplying out everything. This is very technical, but he say, oh, there is such a unique element without telling you what that is. And then he then showed that there is a unique central element in this parabolic subalgebra satisfying some rather crazy equation. So there's some crazy thing happening here. There is a unique central element such as this host. I don't know how to properly solve that. But the craziest thing is that if you compare these two elements, the first one squares to this central element. And this is whose definition? That this algebra is generated by this parabolic subalgebra together with HM. And then you obtain a presentation of this guy.
The third line dot means index is bigger than n.
Right. So
third line.
yes.
Means index is bigger than n.
So to be precise, this is that. This is j greater than n, but you need a double coset. So this is the higher order term. Okay, so I hope you're still with me. This is whose construction, and the problem of this is you can't really do much with this definition because this h, if you don't know, this is not, that's the end of story. But what we recently did is to find a explicit formula for this h, and hence being able to study a generalization of this guy from SM Wreath S2 to SM Wreath SD.
So HM is not center, only CM is in center.
Right.
Oh.
Okay, so let's describe this formula using a normalization. So let me set I is the original standard basis over V. I choose capital I because this quotient looks like capital I. And so you have a new quadratic relation like this. So when I do this, I can eliminate some of this Q power to obtain a nicer formula. And also, you know that I inverse can be determined better without this Q inverse at all.
So V is square root of Q.
V squared equals to Q.
Thank you.
So you need to take a square root of your original parameter. So when m equals to 1, Hm, the extra generator, is actually the standard basis plus its inverse, or its bar. So, and you can compute Zm, which is the square of this guy. This becomes a quantum 2 square. This is indeed central in the parabolic subalgebra because it's actually in the ground field. And for m equals to 2, this becomes a sum of 4 terms. You have I2312 plus I2312 bar. And for example, when I write this, this means I2, I3 times I1 bar times I2 bar. And then I have I23 bar 12 plus 2312 and then 3 squared. So what does this mean? So this is because when I do this quantization, each standard basis corresponds to a crossing of this orientation. Each inverse or bar corresponds to this crossing in the opposite orientation. So when I look at this, this is a crossing of this order, of this orientation. When I bar 1, 2, I am stocking this second strand under the other two crossing. When I'm barring 2, 3, I'm taking the first strand, stock it under the other two. So this is like you take all the possible orientation of such crossings, and then you have to adjust by multiplying something that specializes to 1 when v equals to 1. And sorry.
Could we cook up some new not invariant from your number layer?
Say again.
Not invariant, new not invariant.
I think that's possible. I see that there may be some connection, but I don't know not invariant very well. But if you know something from this, that would be very, very, very nice, fantastic. So, I mean, I don't want to give you the precise
so
form.
You have a general formula for HM.
We do, right.
Okay.
So this is our theorem. Let's not write it down. This is explicit formula for HM and hence ZM. So that makes it nicer in the sense that in the past, who can only talk about the Wreath product SM Wreath S2, but he's not able to discuss a generalization, say sigma M Wreath SD, because using his definition, you cannot compute interaction between, say, this T with that T on adjacent subtrees. Because in the definition, you describe it as the unique element that does something. So there's no way you can compute the multiplication or verify the break relation using this definition. This is only made possible once you have a explicit formula, and this is what we did.
So what about general GM? Always same format? GM, center.
Center, it's in the center.
OM is the Euler form or not?
So
you have equal 1. You have a fixed formula.
Let me say it this way. So this is the center in the tensor product of the base algebra. In this case, when m equals to 2, this is in the center of the parabolic subalgebra generated by I1 and I3. This is actually remarkable. You look at this guy, you say when you square it, you get rid of all the I2s. You can only express this using I1 and I3.
But do you have explicit expression for GM, the center?
So this is, I mean, using the explicit expression for HN, the square of that.
Yeah, I know.
Yeah, but right. So this is, I think, a very nice observation. So you have now a presentation of the Hui algebra. So you have, so I want to really view it this way. I have one base algebra, B, equals to the first part of your parabolic subalgebra. So you are generalizing. You're giving a presentation using B tensor 2. And then you have a, I think I want to use black instead, blue instead. And then you have one H1 that does the job up here. So you your relation is firstly the braid relation of H1, single knot, which is nothing. And then you have a quadratic relation, H1 squared equals to Zm. And Z is some element in B tensor B. So I'm saying this should be the new quadratic relation. In the past, Hicks algebra always have quadratic relations described using coefficient in your ground field, but this is not. We're claiming you should really look at quadratic relations with coefficient in the tensor algebra. And then you have a Wreath relation that swaps A tensor B with B tensor A. And we think there should be some like uniform theory to study any algebra with a similar presentation. And those are the algebra I mentioned at the beginning of the talk. You can actually find a way to describe those affine Hicks algebra and variations using a similar description. And we really hope that this sheds some light of understanding all these. And I think next time I will talk about how you use those general theory to revisit, say, sure dualities for all these types. Okay, for today, let me stop here. Thank you.